Okay, we recently had a Statics 1 multiple choice assignment, and people are asking me, what did they do wrong? Well, I'm going to go over some of that stuff right now. We started the unit with a lab on the force board. We used suction cups or clamps to hold the spring scales onto a table, and they were all attached to a ring. Now here we have a problem where we have two spring scales, and you had to find the missing one. On this multiple choice question, you had to look at the spring scale and read the scale. So let's say this was 10 newtons and 10 newtons. Some people had trouble reading the scales, maybe. They couldn't read the numbers. But the question now is, where's the missing spring scale? Converting the diagram into a force vector diagram, we can see the missing force has to go up and to the right. It would need to have components that would cancel out the original spring scales. You would just have to use the Pythagorean theorem to get the magnitude, inverse tangent to get the angle. So we would say that the force that's missing is 14.1 newtons, 45 degrees counterclockwise from the positive x-axis. Well, there were other questions involving the force board lab, like, did we really need to have paper clips around that ring? And the answer was yes, because you don't want to bind up your spring scales and have a lot of friction. The paper clip allowed for some rotation of the spring scale. There was another question. Does it really matter which way you hold the paper? No, it doesn't even matter if the ring is in the center either. It's just the fact that it doesn't move. What about the spring scales before you even hook them up? You had to zero them. You opened them out of a plastic bag, but it still doesn't matter. You have to make sure they're zeroed before you use them. Doesn't even matter if they were both green and a red one. They're reading newtons. Once you zero them, it's okay. You could use different spring scales. Now, everybody in the force board lab used different angles. They were all randomly placed on the board, and we just wrote down our numbers. We put a coordinate system on the paper and recorded the angles. Everybody added up the force vectors and found an experimental resultant. Well, when we looked at them on the spreadsheet, we saw that they were all very small values. And somebody realized, well, that's because they're all pulling in opposite directions. That ring doesn't move. And we realized that the theoretical resultant should be zero. Everything's pulling in opposite directions. It's canceling out. So if you see an object at rest, we know that the sum of the forces is zero, and that's what we call statics. If these force vectors were given on a problem and you were asked to find the resultant, if this was experimental data, it may not add up to zero. You may have a small resultant. Let's put them tip to tail and we'll see. I moved force vector 2 down to force vector 1. I moved force vector 3 to force vector 2. It didn't quite add up to zero. It didn't quite come back because I graphed this out carefully with a protractor and a ruler. That little resultant should be zero, but it's not. That's what we call our experimental error. And to find that resultant, you would have to break the vectors up into components, add the x's, add the y's. There's lots of videos, handouts with answer keys, my chapter notes. If you're having trouble with this, go study the material that's already been given out and you can check yourself. Kids always tell me, oh, I can do all the handouts, I just can't do the quizzes. That's not possible because these questions are adding up vectors. You got to be able to do it on a multiple choice thing as well. Then we had some questions on the Hammock Lab. Now we did this lab in class and we found out that if these angles are equal, the force on the right and the force on the left are also equal. And here we have the weight of the object going straight down. The x and the y components are laid out. The two y components add up to what the weight is. That's what's holding up the weight. The x components cancel each other out. And we know this because we've learned something from the force board lab, that the sum of the forces acting on this object are zero. This is what we call a free body diagram. You should always get rid of the apparatus. In this case, it would have been two trees, and you get rid of all that, and you just draw the body that all the forces are acting on. Then there were some questions about what happens if these angles get smaller. Well, as you can see, if we pull at a lower angle, we still need to maintain the same y components to hold up the weight. It's the x components that get bigger. It's the diagonal force that gets bigger, but there was a question, what happens to the y components? They stay the same. Well, what's going to happen if this angle gets even smaller? Well, as this angle approaches 0 degrees, this vector here is going to approach infinity. A lot of people said it's going to increase. Now, that's okay, but it's a multiple choice question, and one of the options was to go to infinity. As this angle approaches 0, it will go to infinity, but the y component will stay the same. And there was a question involving the strength of the rope. Let's say the rope can hold 1,000 pounds, and we have an angle of 20 degrees on each side. Well, let's draw the free body diagram. The question is, how much weight can you put in the hammock? Well, all you have to do is take the 1,000 pounds and multiply by the sine of 20. You'll get 342 pounds of y component on this side. Well, you're going to have the same amount on that side. So you can put 684 pounds in the hammock. Now, you can see examples like this all through my chapter notes, all through the handouts, and that's what's on these multiple choice assessments. Then there were some questions about the truss lab. In one of them, you actually had to measure the angle yourself by looking at a grid. We made it simpler and said that the bar here, or the boom, had no weight. So if you could measure the angle and you knew that was 10 newtons, how do you know what the spring scale should read? Time for a free body diagram. Why did I make that the scale pulled? Because it's a string. Strings can only pull. This rod, or sometimes known as a boom in a truss, that's got to push that way on that ring that's on the end of the boom. So now how do we figure out that? Well, look at the y components. The weight's going down. The only thing that generates a y component is the scale. Now, that y component has to be 10 newtons. And that gives us 15.6 newtons for that force of that scale pulling on the end of the boom. Well, you should recognize this as simply going back to the force board lab. It's all the same stuff. Draw the free body diagram and you have 3 forces. They all have to add up to 0. Then there were some questions about lowering the clamp, and that would reduce the angle. We would have to shorten the string to do that. What does that do to the forces involved? We still have 10 newtons going down. So we're still going to need 10 newtons going up. This is the only thing that can produce a y component. And that 10 newtons has got to cancel with the weight. So that means this spring force has to be much larger because the angle is now smaller. Now that means that if this gets smaller and smaller and smaller, your y component still has to stay the same. This arrow is going off the board. It's going to go to infinity. The x component will also go to infinity, but the y component stays the same. Well, we also had a question on the bottle lab, and that just involves knowing how to draw a free body diagram. The weight goes down. The electronic balance was holding it up, and so is the scale. So you had a couple of different forces going up equaling the force going down. Let's just say this was 3 newtons, that was 4 newtons. Are the arrows drawn somewhat to scale? That should have been smaller than that one. And that was multiple choice, so you have to look and see which arrows match up with the numbers. That number would have to be 7 newtons, and it was drawn such that this arrow should be longer than either of those. In fact, if you add those up, this should be the length of both of them together. This was one of my favorites. And yeah, you haven't seen a problem exactly like this before, but we've certainly done all the required basics to get you there. You know that this object didn't go anywhere, so the sum of the forces was 0. What do you know? That x component would have to be equal to the tension in the rope on the left. That y component, well, is it really going to be equal to the weight? There's one more force missing in the free body diagram. It said, what is the force of the floor holding up this cart? Well, if the thing weighed 100 newtons and the y component turned out to be 20 newtons, then the force of the floor has to be 80 newtons. If this x component was 60 newtons, then that tension on the left has to be 60 newtons. Remember, the forces up equal the forces down, and the forces left equal the forces right. Okay, keep in mind that these multiple choice assignments that I give you, there's multiple versions. I am not going to be able to go through everybody's paper individually with you. That's just not going to be possible. So here I am making a video that goes over the generalities. Keep in mind that it's open notes. All of these problems we've done before in some shape or another, and you should be able to find them in your notes, have them at the ready. Maybe next time you want to do is make up a formula sheet so you have a something study guide right there ready to go with you. You really should read my chapter notes. You'll find examples in the chapter notes worked out step by step. Look at the work that you did for these assignments and then find the examples and go for it. Work them out. And of course, you should watch my videos. If I post a video and after a week, there's only say 20 views, that's not looking good when I have 50 kids in the class. So here's a quick example of what's in those chapter notes. It's called a step-by-step guide to learning statics for a reason. It starts so simply. There's a ring. And then we talk about what's going to happen if there's nothing acting on it. You've probably heard of Newton's first law of motion. Object at rest, stay at rest, unless acted upon by an outside force. Well, here's the outside force, a rope pulling, so sure it's going to move. But then what if you want to keep it from moving? Well, then you have two ropes, one pulling one way, one pulling the other. It couldn't start any simpler than this. We go to the force vector diagrams. It's all laid out here very clearly. We go to having multiple forces, 5 and 10. Notice these ropes, the lengths don't matter. The arrows are the lengths of the force vectors. Yeah, they matter. So this would have to be 15. Hey, here's the problem we were just talking about. The two forces at a right angle, what's missing? There's the two forces. Here they are tip to tail. We call that the resultant. And then what's the one force that would cancel them? The equilibrant. So like I say, it's all explained right here. It goes step by step. Here we have a Hammock Lab example. And again, this is all going to be worked out in the details. This is putting the vectors tip to tail. There's the weight. There's the force on the right. Here comes the force on the left. It shows you how to construct a diagram. You've seen these in class. Yeah, and here's all worked out to give you the answers too, so you can check your work. What happens when you start pulling with the angle that's smaller and smaller? This is just an example of what I was talking about. Look at those Y components. They stay the same. The X components are getting bigger. Here's the truss lab. The weight goes down, the rope has to pull. Here's the vector diagrams for the point on the end. Tail to tail, tip to tail. Look, they're adding up to 0. Another thing nice about the notes is it tells you stuff that's coming up in the future. For example, what if the truss had the rope pulling off this way? Do you think that bar is still going to push on that ring? Well, look at this force and this force. They're going to make the ring move over. That bar will now have to pull. We did talk about it when we have the angles that aren't all symmetrical. And all of that is worked out right here in all detail to give you the answers. And here is how we do it tip to tail with the law of sines. And here's the example worked out with all the math. Well, that was the force board. Well, how about a truss? The truss could be angled such that we have two different angles here. And again, this is all worked out in the chapter notes for an example for you to follow. Remember in class, we talked about the words acting on? Well, it depends on which is the object we're talking about. And this is a good review. You should read this too. We're covering tension versus compression. Hey, here's our bottle lab. We have a table, a block instead of a bottle, and we have a rope holding up the block. So it's all right here. If you wanted to learn more and review, right here.